Hey guys, this is Ed with the Kaizen Effect. Today I'm super excited to be delving into a new topic, which is going to be Lagrangian Mechanics, and I'm particularly excited about this one because in undergraduate college this was one of my favorite classes because it was so intriguing and the ideas behind it seemed so revolutionary. And before we delve into the topic we're going to talk about today, which is going to be the backbone of Lagrangian Mechanics, calculus of variations, what I want to do is sort of take a look at history, the backstory towards the development of this subject, because I think it's going to help you understand how it's used, where it should be used, and why I personally thought it was so powerful and such a revolutionary idea to bring into physics. Now, to do this, I'm going to take a look at what Lagrange, who actually invented Lagrangian mechanics, what he was thinking back in the day, and I believe it was the 1800s when this was developed with his peers all around him. Now, back in that day, what they had in physics was just Newtonian mechanics. Basically, everything you would study in Physics 101, you know. In Physics 101, the standard analysis for any kind of system that you're trying to figure out the path of motion or the equation of motion that can describe how the system is going to evolve was to basically put together some free body diagram, draw in your vectors for your forces, your accelerations, your velocities, what have you, and then use Newton's second law, you know, F equals ma, to derive your equation of motion. And then from that, you can get your solution that describes how the system is going to evolve and how particles and different systems are going to react to everything around them. Now, when you start getting into very complex problems, and especially when you go into different coordinate systems, such as polar coordinates or spherical coordinates, the system becomes very cumbersome. It becomes very complex, very convoluted. And this is because Newtonian mechanics with vectors, you know, it's a very Cartesian-based system. And when you start getting into very complex geometry and stuff like that, it becomes very difficult to, I guess, analyze the vectors that are in place, you know, all the different forces, and put together this free body diagram that can help you derive your solutions. It's not impossible, but the amount of effort it takes to actually do that becomes monumental. It becomes very, very difficult. And throughout this course, I'm going to show you guys solutions with Newtonian mechanics and show you how when you take Lagrangian mechanics and the stuff we're going to delve into, how that can drastically simplify your life and everything you're doing, and you're going to see it's absolutely beautiful. But because of this system, because it was so cumbersome, and because it was so hard to translate into different coordinate systems such as polar coordinates and spherical coordinates, what Lagrange did was he took a look at it and he sat down and he said, there's got to be a better way to do all this. There's got to be a way in which I can take all my mathematical prowess, knowledge, and intelligence and put that to work such that we can eliminate these vectors and these free body diagrams and just trust in the math itself. So that was Lagrange's goal. He wanted to develop a system that can give us the same results from Newtonian mechanics by just, just trusting your math, just doing math, pure math. He didn't want to have any diagrams. He didn't want to have any free body diagrams. He didn't want to have to worry about vectors. He just wanted to write down the math with no pictures and then get the results he wanted very quickly, efficiently, and effectively. So that was the inspiration for a lot of people back then. It was for Lagrange with Lagrangian mechanics. And then after Lagrangian mechanics, another simplification came, which is known as Hamiltonian mechanics. That was also the motivation to simplify your life. Because back then, they didn't have computers. They didn't have these algorithms that could, take these differential equations and solve them very quickly and very effectively. So they're always coming up with systems to simplify that. And that's what Lagrange did. What he did was he took his knowledge and he took everything we knew from Newtonian mechanics and derived a new formulation of mechanics that can describe everything in Newtonian mechanics and more, okay? And do that in a very effective manner. So he did this by coming up with very nice results using his mathematics, using his intelligence, and the way in which you want to think about this is he took the difficult part of problems, put that at the forefront in the sense that he figured out all these derivations, all these new formulations, all these new equations that can allow him to get to the solutions he wants at the forefront. So when he's running through problems and he's looking at different situations in which he wants to come up with an equation of motion, he doesn't have to put in a lot of work. He takes the results from all the work he put in up front and then uses that to derive what he wants to get. So now I know you're thinking probably, well, that's great. He came up with this great system that can make my life easier. How did he do that? And how can I take advantage of it? How can I learn what he put his life and blood into? How can I learn this system? Now, to tackle that question, I'm going to do it first philosophically, and then we're going to get into the mathematical framework that's driving it. So the underlying idea behind Lagrangian mechanics is that when you have a system, you have maybe some particles, maybe some objects, the way in which they move and evolve from a physical standpoint is dictated by the laws we have, right? Everything is following Newton's second law. Everything is abiding by the laws of nature that we've derived, such as conservation of mass, conservation of energy, conservation of momentum. And we know that the paths that these objects take, their essential motion has to conform to these laws. And there's no other way. That's just how the universe behaves. So what Lagrange did, he used something that is known as the principle of least action, which is sometimes referred to as Hamilton's principle. And this is a concept I'm going to revisit in the future that I don't think a lot of people can understand because it uses concepts I'm going to derive in subsequent videos, uses an idea of a Lagrangian, but I'm just going to talk about it philosophically for now because I want you to understand the logic that's driving Lagrangian mechanics and how that comes into play with the mathematics, okay? Because physics is sort of like the language or the philosophy of life translated into the language of mathematics. So we need to know the mathematics driving everything in order to understand what we're doing, okay? So the principle of least action basically says there's this path that everything is going to follow such that you minimize the action of that motion, okay? Such that the path conforms to Newton's second law, F equals ma, and the other laws we know, right? Such as the conservation of energy, momentum, and mass, all right? So now another way of thinking about that, which I think helps in deriving all this stuff, is when you minimize that action, it's like we're moving in a way that moves in the most energy efficient configuration possible. The universe likes to move in a way such that we get to the best energy configuration possible, right? We see that in everything in the universe. For example, if I take this eraser here and I have it right here, I move it up right here, what happens is I give it potential energy, right? And the potential energy I put into this puts the system in a less energy efficient configuration, right? Because this eraser right here, it has the force of gravity acting upon it, right? The force of gravity is going down, so it wants to push it down. It wants to bring it closer to the earth, to the floor, right? And if it does that, this potential energy would be converted into kinetic energy. It would start moving, and then eventually it would hit the floor, right? When I go like this, it tends to go into a more energy efficient state, right? We want to get rid of that potential energy that I put into it, okay? So similarly, we see this throughout the universe in a ton of different scenarios. For example, what happened in the Big Bang, the Big Bang originally, right? In that, we had like a ton of mass congregated together, or so we hypothesize. And then one day it blew up because that was not the most energy efficient configuration possible, right? We had so much energy, condensed into this small region. And the universe wanted to move to a more energy efficient configuration. So it blew up and, the mass started to spread out and everything moved or tended towards a more energy efficient configuration, okay? So we know now, as a fact, this is not a hypothesis, that the universe is always expanding. It's expanding. Why is it expanding? It's expanding because it's trying to go into this more energy-efficient configuration. Again, I sound like a broken horse here, a broken record. So we know that the universe is going to move towards that. One extra example, we see this also with electrons when we go into the world of quantum mechanics. We know that if we have this electron that is excited at the outer shell, what it's going to do, it wants to release that energy. It wants to move to an energy efficient configuration. So it'll release that energy as a photon. A photon goes out, and then that electron will jump down to a lower level, which is more stable, right? Things like to be stable. The universe is always moving towards stable configurations, right? We see this with isotopes. If we have, too many neutrons present in that atom, it's going to emit that as electromagnetic radiation such that it can get to a more stable configuration, a more stable atom, right? So this is a principle that we know the universe always tends towards. And what Lagrange said is, he used the principle of least action. He said the universe is going to move in a way such that we minimize the action, or such that it moves to abide by Newton's second law, the different laws of nature. And if we can take all the solutions for the motion paths that these particles or systems will evolve towards, and restrict them to the solutions that conform to these laws, and bring it into the most energy efficient configuration that minimizes the action of the system, then we can figure out the path that these particles and systems are going to evolve towards, okay? And that's the basic idea of Lagrangian mechanics, okay? We're trying to find these paths that we know conform to the laws of the universe. So what he did, he took it a step further. He took his mathematical framework and he restricted the solutions to the correct solutions. How do we do that? Well, the key here is to realize what I just said. We're trying to minimize this quantity that I'm going to go into later, the action. We're trying to sort of minimize the energy of the universe. That's sort of an abstract way of thinking about it. And what does that trigger? What red flag does that raise when you hear the word minimization? When you hear the word minimization, that's the language of calculus, right? That means that we want to take a derivative and we want to set it equal to 0, and that's going to give us extrema for a function that we're looking at, right? When we set the derivative equal to 0, it's going to give us either a maximum, a minimum, or an inflection point, okay? So we want to do the same thing here. We're going to use the framework of calculus to derive the basic tenets of Lagrangian mechanics. All right, so now we have a concrete plan for how we're going to reformulate Newtonian mechanics into this new formulation, which we're going to call Lagrangian mechanics, okay? We're going to try to minimize the action, minimize the energy of the system, so to speak, and we're going to restrict the passive motion that allows us to obtain that. So we want to use the language of calculus because we want to minimize stuff. We're going to take derivatives, set that equal to 0. However, what we're going to find is that the way in which we're going to derive Lagrangian mechanics, we're going to run into a situation that's more convoluted, and I want to illustrate that point now. So in order to do that, I want to make a parallel back to Calculus 101. Back in those days, if we had a function y sub x, a dependent function that depended upon an independent variable x, in order to find the minimum point in this function, what we had to do was we would take dy dx, set it equal to 0, and then we could find the points at the independent variable x, it's not dependent upon anything, at which a variance in the dependent function, the dependent variable y sub x, does not change for a change in the independent variable. I'm going to say that again because that's very important. This is the point at which a change in the dependent variable y, which is our function, does not change for a small change in the independent variable x, okay? Now, if we have a nice function like y sub x equals x squared, that's very straightforward, right? We take the derivative, this becomes 2x equals 0, and we find that point at which we have an extrema is x equals 0, okay? So that's one thing we can do. But in Lagrangian mechanics, if we want to simplify something such as energy or the action, which I'm going to talk about later, we're going to find that it's more convoluted. We're going to find that it's not a function of an independent variable x. Rather, it's going to be a function of a function. And it's not entirely clear how we're going to use the same tools that we've had in Calculus 101 to actually find the minimum point, to take our derivative and, get to that point at which we had the least action, or in a sense, the least energy. Okay? So in order to illustrate this, I'm going to take a side problem and I'm going to derive the basic tenets of Lagrangian mechanics, which is actually one of the most important results, or so I think, in the calculus of variations. Okay, this is an actual subject in mathematics, and it is the language of Lagrangian mechanics. So I think it's important to take some time to actually understand the mathematics, because that's what's going to be driving everything we discuss in the future. So let's actually do that now. And to do that, what we're going to focus on is a problem that we already know the solution, such that our intuition can guide what we're doing and we can learn as we go. So the problem I'm going to work with is the problem of how to find the smallest path, or the shortest path, between 2 points. So let's say we have some point here, which I'm going to call x1, and some point here, which I'm going to call x2. Okay? And from intuition, we know that the shortest path between these 2 points is going to be a straight line, right? It's going to be something like that. However, how do we know that's true? How do we know that's true? Well, in order to figure out how that's true, what we would need to do is we would need to figure out how to determine the length of any kind of curve and then minimize that, right? We want to minimize the total length because we want the shortest path. So let's actually go ahead and derive what kind of function we're going to use for doing that. So we know, maybe you've seen this in Calc 2, I'm going to refresh your memory, that if we want to find the distance from this point to that point along any kind of curve, it could be this, the curve, the solution we're looking for, or it could be something like this. Doesn't matter what it is. What we do is we take a look at a small portion, let's say right around here. And I'm going to blow this guy up. Okay? So we know that if we blow this up, we're going to have let me try and make this a bit more pretty. So we're going to have a small portion here that is we're going to call ds. And then we're going to have portions here I'm going to call dx in the x direction and dy in the y direction. And we know from the Pythagorean theorem that if we want to find the distance ds, we know that ds squared, which is the hypotenuse, is just equal to dx squared plus dy squared. So now, if we want to find the distance of this infinitesimally small portion along this curve, what we can do is we can take the square root. So we get ds, and that is equal to dx squared plus dy squared square root. Now, the thing I'm going to point your attention to is the fact that this function is a function of an independent variable x. Okay, so what we can do here to simplify this a bit is we can say this is also equal to, we can pull out that dx squared. So this is going to become 1 because we pulled that out, plus dy dx, and both of these are squared. So we see that we didn't change anything here because we multiply this through, we get dx squared. The dx squareds are going to cancel, and then we get dy squared back again. So what we want to do is we want to pull this out. So we get 1 plus dy dx squared, and then we pull out that dx. So now we have an equation for the length of this infinitesimal curve, okay? So what do we do if we want to add up all those infinitesimal lengths such that we get the total length along that curve, right? When you hear that term, when we add up the infinitesimal lengths, that should trigger something. That's another trigger word in calculus, right? That raises a red flag. For what? The integral. That's what we do with the integral, right? With the sort of the Riemann sum. So what we want to do is we want to add up all these little ds's. And we can do that by integrating. We can integrate from x1 or, from x1 to x2. So we're going to do that between these 2 points. We're going to add up all these infinitesimal, fragments of the line. So when we do that, we get big S is equal to the integral of x1 to x2 of 1 plus dy dx squared. All right, so now this is something we can use to prove what we're doing, this side story. What we can do is we could minimize this s. We can minimize the length, and when we do that, we could find the path y that is going to give us the minimum length between these 2 points. However, we have a dilemma. Can you see it yet? If not, I'm going to work a bit with this. The dilemma is this guy here, s, is a function of, it may be a function of y sub x, y prime sub x, and also x. So when you differentiate this, there's a problem, right? What do we differentiate this in terms of? Is it ds dx? Is it ds dy? Is it ds dy prime? It's not very clear. We see that we don't have the same framework that we had previously when we were dealing with stuff in Calc 101, right? In Calc 101, we have a nice function. We have a function y sub x that's a function of an independent variable. And we said that when we take dy dx, or the derivative of y with respect to x, and set that equal to 0, we're finding the point at which a small change in the function y sub x is 0 for a small change in the independent variable, right? So we don't have that same thing here. If we did ds dy, it's not necessarily a small change in s for a small change in x. So that doesn't even make any sense. How do we do that? So what we found here is that when we have something which is known as a functional, this is a functional. It's something that is a function of a function. It's not a function of an independent variable. Do you see the difference here? When we have that, we can't use the same framework that we used with Calc 101. Instead, we have to come up with a new mechanism, and that is the basis of calculus of variations, okay? That is what we're going to try to do here, and it's important for Lagrangian mechanics because the action that we're trying to minimize, or another way of thinking about it is sort of like the energy of the system, which is not the full right way of thinking about it, but it helps me in thinking about the systems that we take a look at. We're going to be dealing with functionals. So we can't use that nice framework that was developed in Calc 101. We're going to have to develop something new that can allow us to minimize a functional. And that's what we're going to do now. All right, so now that we know the basic dilemma that we face when we try to derive the basic tenets of calculus of variations, which will be used in Lagrangian mechanics, what we're going to do now is we're going to solve that dilemma. We're going to figure out a way to sidestep this problem and allow us to use the nice framework we have in Calc 101 in an ingenious way that solves this minimization problem. The way in which we're going to do that, and the key to it, is understanding Calc 101. And furthermore, that you minimize something when dy dx is equal to 0. We're going to use that as a guide. How are we going to do that? Again, I'm going to reiterate what I said. When we find the minimum point in Calc 101, what we do is we find the point at which a small change in y, or y sub x, or rather, let me rephrase that, a small change in our independent variable x leads to a negligible change in our function y sub x, right? So when we change x, there's going to be no change in y, right? That's why we find flat points in our function, right? So if we have like x squared, we have something like this. We see the y point isn't changing much when we have a small change in the x, right? And that's when we restrict what we're doing to that point, that allows us to find the minimum point, right? So what we want to do is we want to take the function we have here, our function L, and we want to vary something such that varying that parameter leads to a negligible change in S, and that's going to give us the same thing that we had in Calc 101. It's going to give us that same nice framework, okay? So that's the key to solving this dilemma. How do we do that? We got to be somewhat ingenious. We got to use some wisdom to do that. One way to do that is we want to say that when we change this path, we change the length. So how can we change the path? How can we have that inherent property in this function L? One way to do that is to redefine our y sub x and our y prime sub x. What I'm going to do is I'm going to do exactly what I just said. I'm going to redefine these such that they have a parameter that I can change that will fluctuate this s parameter. How do I do that? What I'm going to do is I'm going to redefine these as I'm going to call them big Y, and I'm going to say that there's an exact solution to our problem, which is the problem of the shortest path, which is in black. So we're going to have this straight line connecting the 2 points. Then we're going to have other options that this S can follow, other paths, which are in red. You know, we can go up like this, we can go anywhere, we can go, whoo, there's any path. There's an unlimited number of paths we can take between these 2 points. So I'm going to redefine this as the correct path, y sub x, plus an arbitrary function, which I'm going to call eta sub x, okay? So I'm going to say that eta sub x can be anything. It can be any function. It's going to be an arbitrary function because when we make it arbitrary, that means we can have any of these paths. It allows us to account for the unlimited number of paths we can possibly take between those 2 points. So I'm going to have this, it's sort of like an error, this eta sub x. You can think of it as an error. So we're redefining the paths we take as the correct path plus an error. And we have to restrict these functions because there's one thing we know that is true about all these paths. We know that the path we take between x1 and x2 has to be such that it goes through the x1 point and goes through the x2 point. Otherwise, we're not connecting the points, right? So we're going to restrict this to be any function that is nice, smooth, continuous, such that we can differentiate it. And also, we're going to say that we're going to restrict eta sub x such that it's continuous, it's differentiable, and it also guarantees that eta x1 is equal to eta x2 is equal to 0. Why does it have to be 0? It has to be 0 because this is the exact function that's already going through here. So, you know, when we have x1, we want to have y at x1. So when we put x1 in here, this has to be 0, otherwise we're not going to pass through that point. Okay, so this is a condition that these guys have to use, and we're going to use that condition later on. It's a very important condition, so take note of that. Okay, so we've got this redefined path, but still we don't have a parameter we can vary such that it varies this s. Okay, because we can't derive this. This is arbitrary, right? Because we want to have all those different paths we can take. So what I'm going to do next is I'm going to put in this parameter epsilon. It's going to be a constant, but it's going to be a variable constant. And when you look at this, eta, we could have any curve here, but when we change eta, this distance in red is going to increase or it's going to decrease. And when that changes, that's going to change the S. And furthermore, it's important to note that we have a point at which this guy is minimum, when the S is minimized. That occurs when epsilon is 0 because that gives us our exact solution right here. So what we see here is that we reduce this down to a function of epsilon, okay? And it's a function of epsilon because this is the thing we want to vary such that we vary this. We have the same framework that we had in Calc 101, right? In Calc 101, I said that we minimize a function by finding the point at which a small change in the independent variable x leads to a negligible change in y sub x, right? That's what we saw with x squared, right? It's that point, that minimum point. It doesn't change when we change x infinitesimally. Well, we have the same exact framework here. Take a look at this. If we change epsilon a little bit, then when we're at y sub x, s is not going to change much, right? But the fact that we can change this and this guy changes directly means we have the same exact framework. We can express this as a function of sort of like an independent variable. So now what we can do is we can take that nice framework and sort of use our Calc 101 ideas and derive a result which minimizes this function out. Let's do that. Let's continue doing that. So one thing we need to do is, since we're redefining y sub x, we have to redefine y prime sub x. So we're going to end up with y prime sub epsilon is equal to y prime sub x. This is a constant, so we get plus epsilon eta prime sub x, and then bam. This is the framework we're going to use to do the same thing we're doing in Calc 101, okay? This allows us to actually do everything I was talking about. All right, so now we have this nice framework that can allow us to use the same tools we know and that we've mastered in Calc 101 with this new problem, with this new dilemma. That's awesome. Let's keep chugging along and see where we end up. So as we see here, as I just said, we have all this nice framework here in which that allows us to vary an independent variable and lead to small changes in our dependent variable that we're trying to minimize, okay? So we have a point in which small changes in this independent variable leads to negligible changes in our dependent variable s, and that means we have a minimum point. That means we can use the same tools we were using in Calc 101. So let's actually use them, okay? What we're going to do is we're going to do exactly what we did in Calc 101 and then see what happens with that. So we're going to say that ds, d epsilon, we're going to set that equal to 0. And then we're going to find a path that allows us to guarantee this condition, right? Because that's what we're really interested in. So how do we do that? Well, when we take the derivative on this function here, what's going to happen is we can bring it inside of the integral because, you know, this is in terms of x and we're differentiating in terms of epsilon. So, you know, we end up with x1 to x2, the integral going from x1 to x2, the epsilon of this function, this L function, which is the 1 plus dy dx squared. So let me just write that out. So, you know, that's also a function of y, which is a function of epsilon. And that is what gives it this nature as a function out. You can't forget that dx. So what we see here is that we're going to differentiate this term here, okay? So we know from, you know, calculus 3, multivariable calculus, that when we differentiate this, we're going to get partial derivatives because of the nature of the terms inside here, right? So let's work with this a bit more. So we're going to have still that integral, and then we end up with dl d big Y, d big Y, d epsilon, plus, so we have to take this part here, and then we also have to do that because that's a function of epsilon. So we also end up with dl dy prime times dy prime d epsilon, okay? And then dx. So one way which I like to think about this, if that makes you very uncomfortable, we say we want to take dl d epsilon. This is sort of it's not a correct way of thinking about it, but when I work through the mathematics, this sort of helps remind me. I say, okay, if we cancel these guys, it's still dl d epsilon, right? Cancel that, we still have dl d epsilon, but we have to account for the changes that each of these variables, I guess, induce into the function, because if we just had this here, this guy, this might change, we might have this derivative here that changes as a result of this, right? When we change epsilon, y prime might change a bit, and that's going to change our L. So when we take the derivative, we have to account for that, okay? That's why we have these two terms here. So what can we do now? What we can do is we can say, okay, well, we can go through our definition here, and we can say, we can take this derivative, right? This guy is going to end up being, well, if we differentiate with respect to epsilon, that's a constant, so we get this eta sub x. So this guy here is going to be eta sub x. And we could do the same thing with this. When we differentiate, again, I showed it in a previous part of this video, we get y prime sub x plus epsilon times eta prime sub x, because we're differentiating with respect to x, and epsilon is not a function of x, it's just a constant, right? So when we do the same thing, here, we end up with eta prime sub x. So if we actually write this out in a new step, just to show us what we end up with, we end up with, what is it? I'm going to put the etas in the front. We end up with eta sub x times the partial of L with respect to y plus eta prime sub x times the partial of L with respect to y prime. So we end up with this guy here. And you might be thinking, well, this is nice. This is nice and all, but what did this give me? What did I gain from doing this? And I hope you're asking that because it's not exactly clear in terms of where we can go from this. But the key to where we go is one of the most important things you can learn from calculus. It's one of the most important tools you learn in calculus. This is actually what my partial differential equations teacher used to bang into our heads, and it's so true. One of the most important things you learn in calculus, especially calculus 2, I believe this is when you learn it, is integration by parts. Integration by parts, because that's used in so many derivations in physics, in mathematics, and what have you. It's such a great analytical tool, and that's exactly what we're going to do. What we're going to do is we're going to try to pull out some kind of function here that can allow us to guarantee this regardless of what we choose for eta sub x. And in order to do that, we need to take this derivative and transfer it over to here, okay? And the way in which that is done is through integration by parts. All right, so let's actually do that. Let's apply integration by parts to see where we can go with this. So what we're going to do is we're going to try again to shift this derivative here over to this guy. And that's going to be done by taking a look at this portion of the equation that we're at. Because we're going to want to restrict this derivative here to be 0. So how do we do that? We're going to take a look at this and we're going to apply integration by parts over here. So what we're going to do is we're going to define these two guys as, this guy's going to be dv, and this guy is going to be u. Because in integration by parts, let me just refresh your memory because some people forget this. What we have is we're going to have the integration of x1 to x2 of u dv, and that's going to be equal to uv defined between x1 and x2 minus the integral from x1 to x2 v du. Okay, so that's the guy we're going to use here. How are we actually going to do this? Well, I guess I could leave that there. So we're saying this is dv and this is u because we want to take this derivative and transfer it over here. So if we look here, we're taking the dv, it becomes a v, so this will become eta here, right? Because when we integrate that, that gets rid of this guy here, and the u becomes du, so we transfer the derivative over to this guy. That's why integration by parts is so powerful. It allows you to rearrange your operations and group things together, okay? That's why I said it's like one of the most important things you can learn from any kind of calculus course in terms of deriving things in physics and subsequent math courses. So let's, I guess, apply this guy, okay? So we have uv, so we get dl dy prime eta sub x, that's defined on x1 to x2, and then we're going to subtract away v du. So v is eta sub x, and it's going from x1 to x2, and then we have du. Now, this is important, okay? I forgot that there because this is important. I guess it's a good thing that it's in a different color because it stands out. So this guy, the du, is du dx. It's du dx. It's this guy. So when we take the derivative, what's going to happen is we're going to transfer this derivative over to that. This derivative is with respect to x. So this becomes dx of dl dy prime. Okay? So now let's work with this a bit. What can we do to simplify this? Can you see what we're going to do here? It has to do with our definition up here. Okay? So it's really nice that we used this definition here in order to conform to our problem. Because when eta of x1 is equal to eta of x2 is equal to 0, what that does is it allows us to say, guess what? This guy here, whoosh, this is 0. It disappears. Okay, and that's very important. It disappears because when we plug in x2, it doesn't matter what this guy is. This guy is 0. And same thing happens when we plug in x1. So that allows us to get rid of our n terms. This is a very important thing. You see this convention crop up every time you use, well, not every time, but most of the time you use integration by parts to sort of move around your derivatives, okay? So that guy becomes 0, and what that allows us to do is it allows us to take this result here, plug it into here, and make some headway. So we can pull out the eta sub x now because ds d epsilon becomes the integral from x1 to x2 of eta sub x. I'm sort of skipping some steps here, so I'm going to come back and explain what I'm doing. We get dl d big Y, and then we plug this guy in here. So we get minus eta sub x d dx dl dy prime. And I'm pulling this guy out here, okay? That's all I'm doing here. So we get minus d dx of the partial of L with respect to y prime And all this is with respect to x. Okay, so this is a pivotal moment. This is when we derive what is known as the Euler-Lagrange equation, which is going to be the baseline for Lagrangian mechanics. How do we proceed? Now, we want to dictate that this guy is 0 all the time. So how can we do that? How can we enforce that quality? How can we enforce that the path y that we choose is always an extrema, a stationary point, and in this case, a minimum? How do we do that? Well, we could say that eta sub x is 0. But we can't do that because if eta sub x was 0, then our configuration we put together would be contradicted. It would not make sense because what we're saying is, this big y function is defined as y sub x, or I guess I could write it down. So we're saying that this guy is equal to y sub x plus epsilon eta sub x. So we're implementing this error to allow us to use the framework of Calc 101. And if we said that eta sub x was 0, everything we did would not make any sense because it would just, this guy would equal that guy. So we can't enforce that kind of quality. What else can we do? Well, we can say that we can take all the possible solutions, all the paths that this system can evolve into, and restrict them to the paths that satisfy this equation here. Okay? If we allow them to satisfy this equal to 0, what is that going to get us? It's going to allow us to keep the framework we have because eta sub x can be anything we choose, but it's going to always make this 0. It's always going to make this guy 0. We're going to get the condition we want, okay? So there you have it. We have the Euler-Lagrange equation here. And what I'm going to do is it might make some people upset, but what I'm going to do, I'm just going to change this variable y such that it looks like the Euler-Lagrange function or equation that you see in textbooks, online, and stuff like that. So it looks familiar. So what we're going to say is, we're going to say that dl dy minus dx of the partial of y with respect to y prime is equal to 0, okay? Now this is a very, very important result. So I'm going to highlight it in red, and I'm going to write down the name. This is the Euler-Lagrange equation. And in essence, what this is the same result in Calc 101 we talked about. This allows you to minimize a function L with L under the integral, okay? And again, let's take a look at what this is doing for us. This is saying that if we take all the solutions, to our problem, all the paths that I guess our system can evolve into, and if we restrict them to the subset of solutions that satisfy this equation, then we're going to find a stationary point, and usually that's going to be a minimum. In the case of Lagrangian mechanics, it's going to be a minimum always. This is the language of Lagrangian mechanics. This is the language that allows us to minimize functionals. And throughout the rest of this course, this is going to be the baby we work with for almost everything we take a look at, okay? So it's very important that you understand how we got this. You understand the underpinning, ideas driving this forward, Because without an understanding of that, you don't understand what you're doing. You can apply this equation in the future, but if you don't understand where it came from and what it's trying to do, then you do not have a full understanding of what you're doing. You do not understand the tool and the power of the tool that you're using. So if this did not make any sense, look over this lesson again, send me an email. I'd love to help you guys out. Just make sure you understand where this mathematical framework comes from. All right, now to wrap up this video and demonstrate what we've achieved with all this mathematics and this final result with the Euler-Lagrange equation, what I'm going to do is I'm going to work through a very simple example that we actually use to derive all this. And that was the example of finding the shortest path between 2 points, points x1 and x2. Now, intuitively, we know what that should be, right? That should be a straight line connecting those 2 points. But how do you prove that? How do you show that? Well, that's done by using calculus of variations, okay? It's using the result we got, the Euler-Lagrange equation right here. That's going to be the essence of what we're going to do. What we're going to say is that all the possible paths we can pass through, it could be an infinite number of amount. But what we're going to do is we're going to restrict the path we want to the path that satisfies this equation, and that path is going to be the path that we're interested in. Now, previously, we derived the fact that if we want the distance between any 2 points along any path, what we can do is we can integrate from points x1 to x2 with this parameter here. And in order to sort of make this work with what we're doing here, sort of use the same syntax, what I'm saying is that this guy here, this square root, that's going to be our L, our function L. That's going to be the L sub y sub x sub y prime sub x, okay? So what we want to do is we want to take this nice result we just derived and use this to find the path that connects these 2 points with the shortest distance. Let's do that now. So what we're going to need to do is, we see here that we need to compute partials. And we're going to see this in Lagrangian mechanics all the time. The hard work is deriving the derivatives. That's the hard work. Once you get that done, you get your equation of motion just like that. You don't have to deal with convoluted free body diagrams. You don't have to deal with figuring out what vectors you use, the different components about that, and that's what makes it very nice. So you see, we use all this complicated mathematics to get this result, but the complicated mathematics heading forward, it's going to guide us in everything we do. We're going to see that in the future. But right now, let's focus on trying to find the shortest path between these 2 points. So the partials we get are dl, dy. That's going to be 0, right? Because we don't have y in here. We only have y prime. So let's actually calculate dl, dy prime. To do that, it's a little messy. We see we get, since we have a square root, we bring down the square root 1/2, and then we have 1 plus, I'm going to start using y prime now, y prime squared. And then that's going to be to the negative 1/2. So we take the 1/2, we subtract 1, remember. It's the product rule here. So then we use the chain rule. So we take the derivative of the inside, which is going to be multiplied by, we have y prime squared. So we end up with 2, not a partial, 2y prime. Okay? So if we simplify that, what we end up with is y prime over the square root of 1 plus y prime squared. Okay? All right? So that's important. We get this guy. We get this guy. So what we're going to do is we're going to use all these results, and we're going to dump it all in here. We're going to take these guys, put it in here, and figure out what that can tell us about the path between these 2 points that minimizes this s. Okay? So when we do that, we get this nice equation. This guy is 0, so we end up with d dx of this, of y prime, over the square root of 1 plus y prime squared equal to 0. What does that tell us? We get this nice result here. It tells us that this guy is constant, okay? It's not changing. That's what the derivative here tells us. So what we can say is that this gives us y prime over square root of 1 plus y prime squared is equal to a constant c. So now what we're going to do is we're going to work with this guy and see if this can give us our expected result, a straight line through those 2 points. If the result we derived here is correct, it better give us that result. Otherwise, it's not working with our intuition and something is wrong here. So we're going to take this guy, come down here, and what we're going to do is we're going to take this, we're going to first square it, okay? We're going to first square this term because we want to get rid of this guy and group the y primes. So we end up with y prime squared over 1 plus y prime squared is equal to c squared. Now, the important thing to realize here is that if you take a constant and square it, you get a constant. For example, if you have 2 squared, you get 4. 4 is still a constant. So what we can do is we could take this c squared and we can write it as a different constant. So I'm going to write it as a. I'm going to write this guy as a. So next, what we can do is, sort of running out of space here. I'm going to crouch down a bit. Don't let that distract you. We can take this y prime squared, or rather the 1 plus y prime squared, multiply it over here, and then group the y prime squared terms. So we get y prime squared is equal to a times 1 plus y prime squared. All right. Then what we're going to do is group these y prime squared terms again, see what we end up with. We go over here. It's sort of all over the place, but I guess this sort of thing happens when you don't have a lot of board space. So we're going to take the y prime squared, pull this guy over, so this is going to be 1 minus a equals a. Okay? So what we can do is we can, again, move that over to isolate this y prime and take the square root. So what we're going to do is we're going to take this guy here, we're going to move it over there, and then we're going to take the square root to get rid of this guy right there. So in the end, we end up with y prime is equal to a over 1 minus a and the square root of all of that. What did this get us? Well, we see that if we have a constant over 1 minus constant, and we take the square root of that, what happens? What happens? We get another constant, right? So we can write this as, and I'm going to use a clever one here. You'll see why. We're going to write this as n, okay? So now, this is the guy we end up with. And let's work with this a bit more. I'm going to erase some of this. Get some more space. What we see is that if we integrate this to get y, so we want y sub x, it's going to be the integral of m dx. All right? When we do that, what we end up with is nx plus b. All right, now that should look really familiar to you. What we see here is that we get the equation of a line, okay? So this guy, this is our slope, and here's our y-intercept. And we see that this complicated result that we derived using some clever tactics to convert this complex functional, this equation here, back to our framework of Calc 101, allowed us to get a result that gives us a result that actually minimizes this quantity here, okay? Because we see that when we worked with this, we restrict our solution set down to the one, y sub x equals mx plus b, that minimizes this guy, and bam, we get the result. We get the equation of a straight line. Bam, we're done. We see that the thing we derived works. We got this nice framework here. We got this nice clever way of minimizing functionals. And in subsequent videos, I'm going to show you how this is applied in Lagrangian mechanics. We're going to use this language of mathematics. This is our language. This is how we're going to talk. Okay, what we're going to do is we're going to see that in order to minimize this thing called action, to make it equal to 0, we're going to have to use the Euler-Lagrange function, and that's how we're going to reformulate Newtonian mechanics to eliminate free body diagrams, vectors, and convoluted processes that are very hard to work with in different coordinate systems. And we're going to see this is going to work for any coordinate system, that it's going to be invariant, and that's what we gained from this. And for that reason, this is why I thought this kind of subject was so intriguing, so absolutely brilliant when I first took it way back in undergraduate college. It was actually my senior year because I was supposed to take it in sophomore year, but I ended up taking it in senior year, and it was really awesome. I really enjoyed it. So I hope you enjoyed that video. If you have any questions, make sure you leave a comment in the comment section below. Send me an email at ed@thekaizeneffect.com. I will help you out. If you want to sit down one-on-one with me, send me an email. We can set something up. I can go over and Skype, help you out, help you out with your homework. I was going to say do your homework. I'm not going to do your homework. I'm going to help you do your homework. And stay tuned for the next lesson, which we're going to talk about some examples in which this is used, and then we're going to apply that to derive Lagrangian mechanics.